you can say this is like with the geometry or the graphical proof. You can say this is something like graphical intuition. Okay, graphical intuition. But we can also have some mathematical proof using a Taylor series. Okay, it's easy proof. Don't worry, it's very easy proof. Just test it for a proof, but it's like worth noticing it. So you might remember the Taylor series. Taylor series if says that if you have the value of the function at x naught, and then you want to find out the value of the function at some nearby point, let's suppose x naught plus h, then you can do like something like this. Okay, or maybe I think we have seen the Taylor series in some other variant, for example. So maybe you might remember that if you want to find out at x naught, you already know, then it is f plus x into x minus x naught plus 1 by 2 f double x naught into x minus x naught whole square and so on. Okay. Now here, if I put, okay, let's suppose instead of x minus x naught, if I put x equal to x naught plus h, then basically it is, okay, this is just a way of seeing it. It is x naught plus h equal to f of x naught plus f dash x naught. X instead of x minus x naught, you can put h. Okay. So it is 1 by 2 f double x naught into h square and so on. Okay. So basically what I'm saying here is that this is the Taylor series formula. It's okay if you don't remember it, right? So the Taylor series formula says that f dash, if you want to find out f of x naught plus h, then it is f of x naught plus f dash x naught plus h plus 1 by 2 f double x naught plus h square into h square and so on. Okay. Now suppose this point, okay, this point x naught plus h is very near to x naught. Okay. So in that case, what I can say that this, if it is very near, okay, in that case, this h cube, h power 4, these terms may tend to 0. If h is tending to 0, then these terms also very close to 0 because h cube is third power of the fraction, right? If h power 4, if I consider h power 4, then it is even very close to 0 because if you talk about 1 by 2, and then if you talk about 1 by 2 power 3, it is 1 by 8, which is very less, right, compared to 1 by 2. So the more you increase the power, the value will keep on decreasing. So what I'm saying, if h is tending to 0, then actually generally it is a good practice to ignore all of this. Okay, it is a common practice actually. Okay, so I can have this as a Taylor series approximation. Now further assume that x naught is a critical point. Okay, critical point means where f dash of that particular function derivative at that particular point is actually 0. In that case it will be 0. Is this okay, everyone? Let me know. If x naught is a critical point, critical, some people call it stationary point or some people call it critical point. You can call it anything, right? Critical. Okay, some people also call it stationary point, which is fine. Now in that case, what will happen? You can directly say that okay, this is 0, right? So what you have is something like this. Okay, so if x naught is a critical point, then you have this something like this, right? Okay. Now from this, suppose I ask you a question. I've written this. Just see this carefully. And if I ask you a question that what should be the sign of f double x naught for the x naught to be the local minimum? Hint is given there that we. Okay, I think I missed. We want f of x naught to be least in the neighborhood of x naught. So if I just ask you, given this relationship, if I just ask you, if I want that f of x naught to be the least, right, or x naught to be the local minimum, then what should be? See, h square is anyway positive, 1 by 2 is anyway positive, right? So I actually want, it is easy to observe, right? I actually want this fx naught to be lesser than anything else in its neighborhood, right? So basically, ultimately what I want is something like this, that f x naught plus h should be actually greater than fx naught. Okay, this is something I want. Okay, because I want to know, I want basically x naught to be local minimum. So in its neighborhood, okay, I want that it should be the minimum. If you talk about the function value at any other point in its neighborhood, then it should be greater. So if I'm looking for this kind of relationship, can you tell me the sign of f double x? Hence, f double x naught should be, I think I should be adding something, isn't it? Should be? Tell me quickly. Greater than 0. Yes, great. So it should be greater than 0, isn't it? And that's what like we have already concluded using the graphical approach. So it is one I can say the Taylor series approach, using which also we can conclude that f double x should be greater than 0. Okay. So you can see what I've written here. I missed to write want anyway, but that's fine. Okay. So we want this fx naught to be the least in the neighborhood of x naught. It's extremely easy. So just have attention here that what I'm saying and just try to grasp the thing. Like even before, if it is easy, then even before I explain it, you should be getting it. Okay. If it is very easy, it's extremely easy, I think, right? If this is the relationship someone give you, and if someone asks you that okay, if this has to be greater, then obviously this should be positive, right? See, this is the relationship, and if I want that okay, this fx naught plus h should be greater. Why? Because this should be minimum. Okay, this should be minimum. If this should be greater, if this quantity should be greater than fx naught, then this can get cancelled out. It should be greater than 0, right? You should be adding something. It's like that, right? You should be adding something. Okay. So it is easy enough to understand. I hope you got it. So therefore, this should be greater than 0. So you can say this completes our proof that x naught to be local minimum, right? So basically, f plus x naught should be 0 and f double x naught should be greater than 0. And hence we proved that using these two, I can say for sure that x naught is local minimum, right? So this is one proof that we will actually extend for the multivariate. So that's why like I thought that we can first have the hands on using a 1D calculus. Okay. Although it was not required for gate CSE, that's why I'm not given it. But I thought that we can understand it because for gate DA we should be understanding little more than and even in the 1D calculus than what is required for gate CSE. Okay. Great. So this is all about the 1D calculus. I just wanted to tell you. Now what about the functions of many variables? Okay. So what we will do, we will extend theorems that allow us to identify and classify local minimizer of one variable functions to the multivariable case. Okay. So let's just see that how to extend these theorems or this first derivative test or second derivative test to the multivariate case. Okay. So you already know what is a multivariable function, right? It is a function of multiple variables. So what is meant by multivariable function? A multivariable